Good afternoon, professors. I'm happy to be here to present our work on the trapezoidal peg problem among convex curves. Now, firstly, let us look into a bit of the classical square peg problem. It was proposed in 1911 by Otto Toeplitz. It asks if every continuous simple closed curve, that is Jordan curve, in the plane can contain 4 points that are the vertices of a square. The problem is still open, and some variations has been solved by topological method. The best result known is by Mestricki, who solved the problem in an open and dense class of curves and for continuous curve in certain bounded domain. So obviously, we could generalize the square in the original conjecture to isosceles trapezoid. It was proposed by Peck in 2010 for piecewise linear Jordan curves. And by some simple geometry, we can show that other kind of trapezoid cannot be inscribed in a circle. So we cannot have the traditional formulation of the conjecture among general trapezoids. But it is interesting to ask, on which occasion can the Jordan curve inscribe an arbitrary trapezoid? So our work is basically on problem 1.1 among strictly convex C1 curves, and we have obtained several results. Firstly, through only translation and stretching, which is a transformation which I'll define later, but without rotation, any given trapezoid can be transformed to a trapezoid inscribed in the given curve. Also, this trapezoid is unique. We can hence obtain a necessary and sufficient condition for the problem among strictly convex C1 curves. So to start with, we dissolve the similarity condition between trapezoid. Basically, two trapezoids are similar if and only if the ratio in which their diagonals cut each other, the angle made by their diagonals, and the ratio of their diagonals are equal. And we call the quantity in the first condition to be the cut ratio, the second condition to be the diagonal angle. We say trapezoid satisfying condition 1 to be quasi-similar and condition 1 and 2 to be semi-similar. Now we immediately have this following theorem, saying that any convex Jordan curve can inscribe infinitely many trapezoids, which are quasi-similar to a given trapezoid T. Now the proof is, the idea of the proof is to assign every point on the given curve a auxiliary curve as the image of the original curve under the homosity centered at that point with ratio to be the cut ratio of the given trapezoid. And we could easily show that infinitely many auxiliary curves can intersect. And for any two auxiliary curve intersects, we consider the base point of them, the intersection point, and the pre-images of the intersection point. And it can be shown that they form a trapezoid with cut ratio T. So the theorem is proved. So before we present our main result, we want to define what a stretching is. Basically, a stretching of a trapezoid, the stretching of a trapezoid is the homosity on either of its diagonals centered at the intersection and with positive ratio. And this is phrased differently in our paper, but they can be seen to be equivalent. So our main theorem 3.2, saying that for any trapezoid and any strictly convex C1 Jordan curve gamma, through only translation and stretching, T can be uniquely transformed to a trapezoid inscribed in gamma, and this way is continuous. So we have some obvious lemmas. Lemma 3.8 is saying that a closed convex curve have exactly two tangents subject to any given direction. And lemma 3.9 says that if we choose two continuous curves with their base point on the pairs of parallel lines of a parallelogram, then they have at least an intersection. So we have this important lemma 3.10 here, that for any given curve that is satisfying our condition and for any vector that is a direction, there exists a unique continuous curve, beta, with endpoint in gamma, such that for any straight line parallel to the direction, either it do not intersect gamma or beta, or they intersect at some oriented given ratio. So actually the uniqueness is obvious, so we could just show the existence. Now we could construct it explicitly, and we put this on some position which we could easily manipulate. Then we consider the two tangent points that are asserted in lemma 3.8. And we join those 2 points, and the resulting straight line gamma at two separate continuous curves, and at some position, both two curves can be described as as graphs of functions, and we consider their weighted average, and the image of it is a desired beta. So we are ready for the existent proof for theorem 3.2. Basically, we consider the two beta with respect to the two diagonals of the given trapezoid with the direction from a larger side to a smaller side. And the two beta can be shown to have an intersection by theorem 3.9 because the four tangent can form a parallelogram, and their point of intersection is not on gamma because if it is, then it is on the end point, but it is still on the intersection. But the curve is C1, so it has a unique tangent. So they have an intersection in the interior of gamma. So consider this intersection, and we cut it through by two straight lines parallel to the two vectors respectively. And they can be shown to intersect gamma as a trapezoid that satisfies all of our conditions. So our existing proof doesn't assert anything about the uniqueness, so we need to prove it separately. And we shall proceed by proof of contradiction. Suppose that two trapezoids satisfy the same condition, and it can be shown that they are semi-similar, and their diagonals are parallel. We can also assume that none of the 8 vertices is collinear because none 3 of the vertices are collinear because the curve is assumed to be strictly convex. So this lemma is also easy to prove, says that no convex curve can inscribe a concave polygon. It can be proved by considering the convex hull of that polygon. So what we want to show is that some point among the 8 vertices can form a concave polygon. So we divide the plane as follows. It can be easily seen that none of the vertices B, D, B prime, and D prime can lie in regions 1, 3, 5, and 7. Because if they do so, then we connect them with the 4 vertices shown here, which is A, C, A prime, and C prime. They form a concave pentagon. So the rest of the cases, for the rest of the cases, we shall use some kind of exhaustion. We shall exhaust on the regions which B prime can belong to. And I think we have a limit of time, so we will just show the illustration here. Now this is for region 6, region 4, and region 2, and region 8. So after exhaustion, we could see that B prime can lie in none of the 8 regions. So this is a contradiction. So we have proved theorem 3.2. So there is an interesting corollary of it, which gives a partial answer to problem 1.1. Firstly, we define a trapezoid to be with diagonal ratio delta if the ratio of its diagonal under some orientation is delta. We use this phrasing because actually it can be with different diagonal ratios. So corollary 3.17, which partially answers problem 1.1 among our class of curve, saying that a trapezoid can be inscribed up to similarity to a given curve satisfying our condition if and only if the curve further inscribes 2 other trapezoids with the diagonal ratio with the original diagonal ratio bounded by them. So the proof of necessity is obvious. We could just take the original trapezoid, and for sufficiency, since our theorem 3.2, the way of inscribing our theorem 3.2 is continuous, we could use the intermediate value theorem to show the results. So here are some other corollaries. Firstly, there are uncountably many trapezoids that are semi-similar to a prescribed one can be inscribed in a curve. We could just rotate the original curve to obtain them. And also, theorem 3.2 is true for generally strictly convex curves with probability 1, because the only place where we need differentiability is unique tangent, and a strictly convex curve have unique tangent with almost everywhere. So,
what do you mean by semi-similar?
Maybe I go back to that slide. Semi-similar is 2 trapezoids with the same cut ratio and diagonal angle. sorry. Yes. Yeah. Semi-similar is a pair of trapezoid that's satisfying condition 1 and 2. Loosely speaking, it's two trapezoids with their diagonals cut at the same ratio, and the angle between their diagonals is the same.
Okay.
So, okay, yeah, okay.